Okay, I was looking at this LinkedIn post from Kronoslav Popovic. The guy is a software developer and mathematician. He developed this algorithm, which is the way that we learn how to do things, but to compute 2 to the power of 10,000. That is the way that we learn in school. There is a way that we learn in school, but he does it differently in a reverse way. And I like this kind of posts because despite the fact that in this current form, they are not going to be used in a practical way. You can learn ideas, these gotchas, that then you can expand and implement in a more efficient way in exploiting assembly or vectorizing or doing a more technological approach. But it's very interesting. I recommend you to have a look at it. And of course, being technology addicted like I am, I had to take. I have to give my take on this, and not only I did once, I implemented several. I had several implementations of the same algorithms and improving performance, improving the reach of the algorithm from 2 to the power of 10,000. We are computing 2 to the power of 10 million now, and it's very cool. It's something that you can do with other languages too. And by the way, this is something that's built in Python. Python does that with the Python Big Num library, and it's very efficient. So if you wanna try it out to compute 2 to the power of 10,000, just open up a Python shell and type print 2 star star 10,000, that's 2 to the power of 10,000, and enter. You should have something like this here, with 3011 digits. It's a huge number. We just with some of our implementations we did 10 million, 20 million. Then it's possible. So the code that I wrote with the improved versions of it is in my GitHub. It's HFTrader. Stands for either my first two initials or high frequency trader, and my paste bin. So it's in my paste bin. There's 1, 2, 3, 4, 5 versions of it. First version is the serial one. It's very simple. It's just computing the blocks and computing the carry and bring it on. The second domain divide is a threaded version where you divide the blocks for each thread. There is domain divide template, which is the same thing, but the actual function that the thread executes on is a template version. So we attempted to do some template tricking just so to see if performance increased, but there was not much difference. There is then the multi-threaded x86-64, where we have instead of blocks of 32 bits, we use blocks of 64 bits. But when we do that, we have to compute the multiplication and division of 128-bit numbers and that requires some assembly because there is no support for that in C or C++ intrinsically today. Then we have all right, and then we have the last one. It's the pipeline version. This is more the what you would do in FPGA in RTL. You would set every you set one. There is no thread in an FPGA, but it's one execution line for each block, and keep moving as a pipeline, like in a production line. And the problem with this version is that it's too slow because of contention. So if every block you compute, you have to synchronize with the next one, and that synchronization doesn't pan out well in a modern processor. You have to have you can't control contention at such fine-grained level. You have to have big chunks of data to be worked on and then synchronized. That's why the domain division, these two, the first ones, they have a better performance, but still not as better. I mean, not much better than the serial version. I think it's the maximum with 4 cores. The maximum improvement I could have was 2 times the performance. But it's not a one-to-one. There's a lot of still contention is still a big issue, even if you have big blocks. And the serial version is actually my preferred because it's very simple and it performs well, and it performs at the same speed as Python as well. So if you take this version, the compute power 2, and you time it against Python, you do, for example, time Python -c open quotes print 2 to the power 6 of 10,000 and end quotes. If you do that, it's gonna give you the same execution time as running this particular version of the algorithm. So what I wanted to do really